Hi everyone. So today's topic is surfaces of revolution. So what are the surfaces of revolution? These surfaces are a collection of curves arranged in a specific manner which are rotated about a specific axis. Revolution of a curve means rotating its every point about the axis, taking the axis as the center. For ease, I take them as the x, y, and z axis. So how do we represent these surfaces? We represent them with the help of mathematical equations. We can write these equations in three forms, which are the cuboidal, cylindrical, and the spherical coordinates. So let's start and try to write a few of them. So topic's name is surfaces of revolution. So I will take a few examples. I have the x, y, and the z axis. X, y, z, x, y, z. Now, the first example which I take is a sphere. Which is formed after rotating a circle about any of the given axis. I have a paraboloid formed by rotating a parabola about the y-axis or the x-axis. I'll correct this, it's y and this is it. So I have the third example is an ellipsoid formed after rotating an ellipse about the x or the y-axis. Now our task is to find the equation of the surfaces of revolution which are formed after rotating the given curves about the y or the x-axis. So let us take a case which is a curve. Let's say its y is equal to fx. So this is a fx, x and y. I rotate it about y-axis. So it will be this, the surface of revolution. I rotate it about the x-axis. So the surface will be somewhat like this. So what are the equations of these surfaces which are formed after the revolution? So I'll write the formulas and then give the explanation. So the formula for the rotation about y-axis is y is equal to f of root of x square plus z square, and for the x-axis is this is about the y-axis, and for the x-axis is f of x is equal to root of y square plus z square, or the z-axis about x-axis. Now let's see the explanations behind these equations. So I have a curve y is equal to fx which has been rotated through, say, y-axis first. So basically at each of these curves, every point is rotating about a circle which is centered at this axis. So the curve, the surface which is formed, which will be this. So let's try to find this equation. So basically this curve is taking its image in every plane which has been hinged at y. So basically these are the family of curves or the family of planes which are rotating about the y-axis, or which have a general line in common, which is the y-axis. So I'll try to show this plane. It is somewhat like this plane, which has been hinged at the y-axis, and we have a curve over this plane which is rotating about this y-axis. So for every single point, say I draw this vector here, say it is pointing towards x-axis here, which is x0, 0 point, and the height, and if I put this point in the fx, it gives the height y. Or at every plane, this point can be this vector which is contained in this plane, which is pointing towards x, 0, z, and the magnitude of this vector gives the height y. So basically height y is f of root of x square plus z square. Here x square plus z square is the mod of, say, it vector v. So basically f vector v is xi cap plus j cap plus zk cap. So the mod of v is root of x square plus z square. So y is this. So let's see for x. So I have a curve fx. So let's take this for x-axis. If I rotate it about the x-axis, the surface which is formed will be like this. So let's see the explanation behind the equation of this surface. So I have a height y. Basically the height y for this curve is, let's say this is the xy plane. I have a height y. I have a y vector which is pointing towards y-axis, and here its coordinates is, let's say, 0, 0, y. As the curve rotates about the x-axis, now let's say it is rotating about the x-axis, every point it also rotating. So basically the height y is being changed at each point as the y changes. So at every point this vector is also rotating. So in each rotating plane, this vector will point towards, say, it 0, y, z, and the mod of this vector, if we put in the function, the inverse of the given function, it will give the point x. So basically here, if this is the x and say this is the point f of inverse of y, so basically in xy plane where z is 0, x equal to f inverse y. For this plane, or for a general plane, I have, for general plane, I have x equal to f inverse of the mod of this vector. So let's say this vector is y j cap plus z k cap. So mod of this vector will be root of y square plus z square. This is mod v. So f inverse of mod v, which is root of y square plus z square. So this is the equation for rotating each curve about the x-axis. So these were the locus of the points for each curve, or the locus of these curves for each point which are being rotated about the given axis. So let's take some examples for easy understanding. So I take an example which is, I take a paraboloid which has been formed by rotating parabola about the y-axis. So I have this parabola in the xy plane, and see this is being rotated about the y-axis. So this is a paraboloid. Let's say the equation of this parabola in the xy plane is y is equal to x square. So fx here is x square. So let's find the equation of the surface. As it is rotated about y-axis, the equation of the surface is y is f of root of x square plus z square. So basically it is y is equal to f of root of x square plus z square whole square, which is y is equal to root of x square plus z square whole square, which is x square plus z square. So this is the equation of this parabola. As it can be seen that on putting z equal to 0, which is the xy plane, or cutting the cross section of this paraboloid with the xy plane, the equation we get is for the parabola, which is y is equal to x square. So let's take example 2, which is rotating a circle. Say this is the circle X, Y, and Z about the x-axis. So basically it will be a sphere. Let's say the equation of this circle is x minus 1 the whole square plus y square is equal to 1. So basically this circle has the center at 1, 0, 0 and a radius is equal to 1. So as this circle is rotated about the x-axis, the equation here we know that f of x is plus minus root of 1 minus x minus 1 x minus 1 the whole square. So f of inverse, which is x, that is the equation for this surface which has been rotated about the x-axis. So the equation is x equal to f inverse of root of y square plus z square, which can also be written in the form f of x is equal to root of y square plus z square. Fx taking from the equation 1 plus minus root of 1 minus x minus 1 the whole square. This is equal to root of y square plus z square. As the root of y square plus z square will always be positive, so we neglect the negative part, that is the lower half of the circle, which is a semicircle. So basically if I do the square, if I square the both sides, I have the equation as x minus 1 whole square is equal to y square plus z square. Hence the equation of this surface is x minus 1 whole square plus y square plus z square is equal to 1, which we already know is true for this sphere centered at 1, 0, 0. So that was all from the surfaces of revolution. Thanks.